All right, so here's the thing. The most important thing about polynomials and the thing that we're going to spend the most time on and the thing that we're going to start doing right now is finding places where the graph crosses the x-axis when you're looking at a polynomial. And so you remember when we were just doing those problems with the polynomials that look like this, and we were looking for this spot and this spot and this spot. Those were called the zeros. They're called zeros because they're solutions to this equation, and p of x is just any polynomial. And so that's why they're called zeros on the calculator. But they're also solutions to equations, and so we're going to start doing a little bit of working with getting the solutions to the equations. So here we go. A lot of this actually comes from what we know about quadratics already, and so I'm going to do something on this polynomial equation that you might have seen before. What I'm looking for is a common factor. So this is sort of the first things you can be looking for when you're solving these equations. Is there a common factor you can factor out? And there is. There's an x in each of these things. And so if I rewrite this, I could write this as x times some stuff. And the stuff in here, when I distribute the x back through here, I must get this again. So I have to write, this has to be 3x squared. This has to be minus 11x. And then this has to be plus 6 equals 0 because it's equal to 0 over here. So, hey, wait a second. I have two things multiplied together by each other, and I get 0. And all of a sudden I can say, I can use the zero product property. So everything we're going to use this unit comes directly from what we did last unit. And so if you're not super for sure 100% ready for this because you're not super comfortable with unit 4, then you got to email me, you got to talk to me because we got to make sure that we're in good shape for this unit. So what we can say is x is 0, or we can solve the equation 3x squared minus 11x plus 6 equals 0. And you were just thinking that you could get away without having strategies to solve this equation. Well, check it out. This is a quadratic. It's equal to 0. You can factor it. You can use the quadratic formula. You can complete the square. You can do all these different things. For our purposes today, it looks like this problem is factorable. And so I'm going to say AC is 18. B is negative 11. Looks like I'll need to use negative 2 and negative 9. So box method, here we go. I know it's like a throwback. 3x squared, 6, negative 2x, negative 9x. Probably got to have a 3, maybe a negative 3 here. Probably got to have a negative 2 here. That means that I've got to have an x here and a 3x here. So my factoring for this problem is 3x minus 2 times x minus 3 equals 0. I'm going to write that equals 0 over here. So, hey, check this out. I should zero product property this also. So now I have 3x minus 2 equals 0 and x minus 3 equals 0. So hold on a second because check this out. 1, 2, 3 equations. This one is done, so I don't have to do anything here. But this one I'll get x equals 2/3. I'm speeding through this because this is stuff that you are already ready to do. You're already comfortable with doing this, so then you get x equals 3 over here. Hey, look, 1, 2, 3 solutions. So I'm going to just highlight everything that we know. This spot, and this spot. Check this out. We have 3 answers to this equation. This equation has solutions here, here, and here. And more than that, what's important with this is now we have some intuition about what the graph looks like. I feel like Sal Khan when I say intuition. When we solve this equation, we're looking for the x-intercepts. And so one of the x-intercepts is at 0. One of the x-intercepts is at 2/3. And the other x-intercept is at 3. And so you'll probably kind of start to get used to looking at this stuff, but eventually you're going to figure out that cubics either look like this or like this. And so this one is going to look like this. How do I know that? Practice. If you don't know that yet, put it in Desmos, see what it looks like. There's no shame in doing that. I just want you to start to see relationships between the equations and what the graphs look like and what the solutions to the equations are. Next one. Hey, this one is already factored, and that means that we can just go directly to the zero product property. So let's take a look at that. What we can say is we can say 3x minus 2 equals 0. Say x plus 8 equals 0. We could say 2x plus 7 equals 0. And we could say 5x equals 0. I'm going to just kind of separate these things out, and we'll get there's that one. There's that one. Okay, so here are my 4 solutions. 1, 2, 3, and 4. And so somehow I have to represent the fact that this graph is going to cross the x-axis in 4 different places. It's going to cross the x-axis at x equals 2/3. It's going to cross the x-axis at x equals -8. It's going to cross the x-axis at x equals -7/2. And it's going to cross the x-axis at 0. Okay, so somehow this graph is probably either going to look like this, or it's going to look like that. Probably not. It's not going to be squiggly at the end like that. Something like that. You can put this in Desmos and see what it looks like, but it should look something like, someday I'll get good at this. That, more or less. Okay, we can figure out the x-intercepts by solving this equation, and you can figure out basically what does the graph look like using that information. Okay, what I want you to do right now is I'm going to have you pause this video. I know you're in Nearpod right now. Pause the video, open up a new tab, and type in desmos.com/calculator. In 2 separate lines, you're going to type in this one and this one. And I want you to go back to Nearpod after you do that. Look at the graphs, maybe change the window, maybe, zoom in or out, whatever you got to do so you can see it. I want you to answer these 2 questions. What do you notice? What do you wonder about? I want to hone in on the spot on the graph, -6, 0. So keep your Desmos open in one tab and come back to this as we go. Here's the thing. What is happening at -6, 0? That's right here somewhere. I'm wondering, does one graph cross but not touch? Like that, or like that, there. And does the other one bounce? And you should see that the equation called, or the function called p of x touches but does not cross the x-axis there. So it probably looks like either like this or it looks like this right there. That's important. Let's compare that to q of x, because q of x probably crosses like that or like that there. And so there's a difference there. And what I notice is that the only difference in the equations is that p of x has 2 factors that say x plus 6, and q of x only has 1 of them. And so that is important. The reason that the graphs are different and the reason that we have different things going on in them is because of what I just said. These 2 things are different. P of x has like a perfect square right here. It's the same thing multiplied by itself. Q of x only has 1 of them. And so because of this situation in P, we can say that there is a solution at x equals -6 for p that has multiplicity 2. What that means is, first of all, you can see that because it has two factors that say x plus 6, and you can see that on the graph where it bounces but doesn't cross, okay? And so I should draw that better like that. Okay, so two ways of describing this, and I know that this is maybe not the most important thing, but I just want you to see it and hear the words. We can say p of x has a double root at x equals -6, and we can also say p of x has a root at x equals -6 with multiplicity 2. These two things are interchangeable. They mean the same thing, but you might hear me say those words a couple times this unit. We can see that because the factors are written twice. Remember that if we were solving the equation p of x equals 0, we could use the zero product property, and we would split up x plus 6 equals 0, and then we would say x plus 6 equals 0, and we do it twice. Because we're doing it twice, we call it a double root or multiplicity 2. If we did it 3 times, we would call it multiplicity 3 or a triple root. Well, not really formally, but one of the ways we can explain multiplicity is the multiplicity of a factor is the number of times that x minus whatever shows up. You can also say it as the number of times that you get a solution x equals a when you're solving. Okay, that's kind of a lot of words, kind of a heavy lift on vocabulary today, but I need you to kind of be able to talk about polynomials right away so that we can be consistent about how we do this throughout the unit. So a lot of vocabulary here. I'm just going to run through it one more time. We have names of polynomials by their degree: constant, linear, quadratic, cubic, quartic, quintic, and then after degree 6, we just say degree 6 polynomial, degree 12 polynomial. As far as your end behavior goes, that is what happens on the left side of the graph or the right side of the graph. You can either have up or down in both directions. Your turning points are where the graph goes from increasing to decreasing or from decreasing to increasing. Your zeros are the places where the graph crosses the x-axis, here and here maybe. And then maybe there's one more. Multiplicity is the number of times that a factor shows up in an equation, or the number of times that you get an answer out when you're solving. What that means is how the graph crosses or touches the x-axis matters. Okay, so there's sort of the vocabulary for the day. I think I am done talking finally. Have a great day, work hard, see you next lesson.